I'm Christine, and I have the pleasure of introducing Dr. Yair Rosenthal, who joins us all the way from New Jersey today to speak on climate change and the ways that the oceans affect it. He was born and raised in Israel and attended the Hebrew University, where he had his undergrad in geology and biology and his master's in geochemistry. Shortly after that, he moved to the United States and did his Ph.D. at MIT and Woodsville Oceanographic institutions, where they have a joint program in oceanography. He did some postdoc work in the biosphere too, in Arizona, studying the effects of CO2 fertilization and ecosystem photosynthesis. And then he took a position with Rutgers University, where he served for the past 25 years as a professor and department graduate program director for the Department of Marine Science and Earth and Planetary Sciences. Most of his research is focused primarily on climate change over time and different mechanisms behind it, especially the roles of the oceans planet. He's introduced. Welcome, Dr. Yair.
Thanks a lot for inviting me. I had a great lunch with students. It was really fun talking to them. I would say we should do it more often, but I'm not gonna. But it was a real pleasure. I did mention their serendipity, and one of that is many years ago, Shimon, who was my TA actually in geology, say when I look what to do, he said, why don't you do a PhD in the US? I said, I don't want to do it, but he said, just send your application. So I sent, and now I'm here. So you never know. Anyway, the talks that I'm going to talk is Paleoclimate perspective on climate change in the Western Pacific warm pool during the Holocene and last interglacial. So my whole career, essentially, not whole career, but over the last 2 decades, I was trying to look for different analog to what may happen in the next century. What you see over here is 2 things. One is on the left is the primary drilling ship of the US, the JODIS Resolution, that replaced the Global Challenger. Those of you that know about plate tectonic, deep sea drilling, essentially started by deep ocean drilling to validate the plate tectonics. And what you see over here, I'll show you again in the background. This is when we work in 2016 near Papua New Guinea. Notice that the islands in the bottom and then the clouds. The clouds are the hallmark, essentially the Western Pacific warm pool. So the question that we start, 2 questions. Why the Holocene and the last interglacial, and what are they? So what I'm showing you here is essentially changes in temperature, if you want, showing the changes between warm interglacial and cold glacial periods. On the left is the present, on the right is 1 million years ago. So warm is upward and cold essentially is downward. The Holocene is the recent interglacial over about 11,000 years. And the previous one, around 127 to 118,000 years ago, we call the LIG, or the interglacial. Those both have periods in the beginning that arguably were warmer by anywhere from 0.8 to 1 degree centigrade, which is what essentially we are seeing now with global warming. So one of the questions that many of us are asking, let's look at those periods and see what the climate response, things like what was the sea level, precipitation, distribution of temperature, so on and so forth. So this is one of the motivation. And then the other question is why the Western Pacific warm pool, or as we like to call it, the WPWP, or Indian warm pool. So let's look first in the, as I said, about, the first question. And what I'm showing you here on the left is essentially temperature change in the last 50 years. And what you're going to see here, so this is mean annual temperature. I'm talking about, and a lot of things that I'll mention is mean annual versus seasonal, okay? So you can see that the mean annual temperature is essentially warming up quite a lot. And it's mainly in the high latitude, in this case, northern high latitude, things that we like to say as polar amplification. On the right, we see some sort of a prediction, future temperature. Warming depends on choices today. So you can see, and it really depends both on population growth, but also on how much emission we're going to have. So, substantial cuts in emission that, we're talking for a long time. We haven't seen that. And even if we cut, emission now, there will be enough heat essentially in the pipelines of committed heat that we'll have. And the temperature is going to increase anywhere between 1 to 3 degrees. Our models are kind of limited by the climate sensitivities that we have. So why is it important? Well, it's important for many things, but one thing that probably concerns people around here is that sea level is going to rise due to at least two factors. One is the thermal expansion due to the increase in temperature. The other is melting of the ice sheet. So again, there is a lot of effort by paleoclimatologists like myself to look at the sea level in response to changes in temperature that we have. Yet determining what was exactly the temperature at the time and the sea level turned out to be complicated. This is a paper that Andrea Dutton did in 2015. When she was in the University of Florida, so Floridian, and showing essentially what we have. So after the Industrial Revolution, we have about almost 1 degree warming. And maybe it's comparable to what I call the LIG, last interglacial, that we think was about 1 degree, but I will challenge it over here. And then, other periods, so MIS stands for marine isotope stages. So a warm stage 11 around 425,000 years ago, we think the temperature was about 2 degrees. Some people think it may be later. And then about 3 million years, the world was warmer by about 2 to 3 degrees in a period called the mid-Pliocene warm period. So all this turned out in the last 15 years as a target for paleoclimatologists trying to see, whether we can verify or validate essentially the estimates of warming and that what was the climate response at that time. So papers like this one in a review article in Nature Geoscience, paleoclimate constraint on the impact of 2 degrees anthropogenic warming. So notice, just to show you without, we have 2 time scale. One is over here, the upper figure from 0 to 12,000 years. And what you can notice over here at the blue one is essentially the temperature. Delta T is the anomaly. A lot of the stuff that we are talking is in anomalies, in this case, between 1850 and 1900, okay? That's not always the anomaly, I'll show in a second, but this is how they define it. So that's the common era at that time. And notice that around, let's say, 10,000 years to about 6,000 years, here you can see a warm period by about less than 1 degree, and that's what is known as the Holocene thermal maximum. So again, that was one target to look what happened in the early Holocene prior to human intervention or perturbation of the carbon cycle, and let's see how climate responded. And then the LIG, around 125,000 years ago, again, you can see the temperature is warmer by maybe 1 to 2 degrees, and those are the data that people have provided. So looking at this dimension is a confusing thing. So the temperature reconstruction are much more complicated. What I'm going to run for you now is a recent compilation. So this comes from NOAA, essentially of changes in sea surface temperature is anomalies. The anomaly in modern climate that we're looking is between 1960 and 1980. And the reason that the temperature didn't change much, and happy later to discuss why, but everything below that will be negative, everything above that will be positive. So we are taking this one as Miocene period as the reference. So I want you to look at what happened with time, but also especially in terms of the distribution of climate, and that will give some idea on, how temperature is increasing. So notice that clock is going, at the top. We're getting into the reference period, not much change. And we're getting to the picture. So I hope you got the idea that first, the warming is not going to affect everywhere the same, okay? Some places will be affected much more, and that's including, for example, Florida. But a lot of that will be in the polar region, the polar amplification, but almost everywhere will be affected. And since the 80s, essentially, when before that we have some sort of a buffer, which called global dimming, that's essentially pollution prevented warming much higher. But once we clean the air, we're getting the full effect of the change. So we're seeing from the 80s, essentially, and this is 2021, we are actually in much worse situation right now. So the second question was, why the warm Pacific warm pool? So this is an area of sea surface temperature, the warmest in the world. So it includes essentially, if you look at the broader sense, it's the Indo-Pacific, and you can see that the temperature, by definition, exceeding the 28 degrees. Really warm temperature, right? Something that you guys got this summer around here. So the warm temperature imply a few things. One is, it is essentially the heat engine for the planet, both as visible, but also as latent heat. And essentially, let me talk about that first, about the temperature. So if we're looking, for example, at what I told you about the reference period over here that you can see, and the negative anomaly before the 1940, 1950, you can see that we are now almost at 1 degree warming. So we are really, really warming. But this is just, the tip of the iceberg, because the real iceberg is essentially in what we call the ocean heat content. So the ocean, water has a very large heat capacity. By the way, stop me anytime if you have questions, but please don't hesitate. I should say that, people. So the ocean, if you give it enough time, will take most of the heat. We don't give it enough time, but it's still taking a lot of the heat. So you can see it here, the ocean heat content. So how much heat in calories we have here is in joules. 10 to the 20 is a very large number, Z-touch joules, we call it. But you can see that there is almost, linear increase, a lot of the heat going into the ocean. And that's kind of the buffers that we have from essentially warming of the atmosphere. The atmosphere has very little compared with that. But here is a measurement of ocean heat content in the ocean in the thermocline. So in the first few hundred meters that you see here, and notice that those warm color is where heat is taken into the ocean. Since 1950, we have those measurements. And I just want to make sure that you see over here, so the region that I'll be talking a lot, the Western Pacific warm pool, you can see this warm, area. This is an area that takes quite a lot of the heat, but it's just area that is not necessarily stable because of dynamic changes in climate. So sometimes the ocean can change circulation, I'll show you in a second, and can release heat, sometimes takes more heat. So it's not just what happened when we release it. The ocean has a huge role in the global temperature. Again, just to tell you, atmosphere has no memory. There is no heat capacity of here. But water has it, so the memory and the ability to change our climate is in the ocean. The other thing that I mentioned is that this is also the global steam engine. So those of you that don't know, most of precipitation on the planet occurs in a very narrow band. It's called the tropical rain belt, or the ITCZ, Intertropical Convergence Zone. That's the area that essentially the winds are coming near the equator and then they rise up. As they rise up, they basically take a lot of moisture. And I don't have to tell you about humidity. You are in Florida and here. Warm air takes a lot, can have a large saturation. So that ends up that where we are interested is most of the evaporation that happen on the planet. This evaporation moves the moisture essentially, so precipitation elsewhere, but also latent heat. That's what's basically the conduit for heat on the planet that we have. So there is a large interest today, what will happen to the rain belt under different scenarios. And those scenarios can vary. So just to remind you again what I mentioned, this is a map essentially of the winds on the planet with the different circulation cell that we have here. So the equator over here in the middle, and you can see the ITCZ, that's the belt. That belt I'll mention later is moving seasonally. That's why we have rain and dry season in the tropics essentially. Or now we're talking about the tropical rain belt. And you can see that their circulation is such because the air pressure that the air is coming up essentially the tropics and bringing this moisture, and then it goes toward the two, polewards in both sides, dump the rain wherever it dump, and then when it subsides, essentially that's the mid-latitude, that's the desert, it's dry, so on and so forth. So we have two major wind circulation over here. The equator to pole, we call it the Hadley circulation, and then the zonal from the east to west, we call the Walker circulation, and I'll mention that later. So again, just to show you, this is one of the times that we have. You see this cloudiness and rain. That's due to what we call deep convection. That's essentially the intertropical. The air is warm and it's lifted basically and take all this moisture and then dump it essentially as precipitation. So my interest there, I was telling, first, I like this region, and I said, I like the food, I liked everything, so I decided I want to work there. But also, truthfully, I mean, we are talking with area that is the densest human population in Southeast Asia. So the impacts are huge. And even though many people don't know about that, the consequences to all of us will be really major. I mean, we talk about India over here, and then Southeast Asia, China, and of course, Indonesia. There's Borneo and Papua New Guinea, which is not the same. The second thing is that vulnerability to climate change is also very large there, and we not totally understand it. For many reasons, the models are not doing very well there. I'll show you. Because of the complexity of the region. It has the effects of monsoon, it has the effects of I'll mention in a second, El Nino, anything that you want happen in this region, and we don't know all the constraints that we don't have on this region. So again, that was one of the reasons that I wanted to go there, and just to give you just taste of what's going on there. So here is just a selection flooding I believe this is Jakarta. This is definitely in Jakarta. It happens again and again and again every year almost. And then we have huge fires in Borneo, Kalimantan, Java. If you check, it's not just human. I mean, they have lung disease, but also what got really the attention of the orangutans that they're trying there. So animals, is a big issue there. You can see what happened here in the orangutans. I mean, it's really invisible. And then, all the liquidation of soil, huge problem. I'm not going to talk also about the change in sea surface temperature has a major effect on coral reef. Same here and everywhere else. You get coral bleaching. And just to remind you, that the world fastest thinking city is Jakarta, which is relocated. I mean, just imagine, we are relocating a huge capital, 20 million yen. So the question that I asked is what drives variability in temperature and rainfall and convection in this area, and what may be the effect on human? That's one thing, ecological system. I know you guys have a lot of ecologists. I'm not going to touch on that, although we did something on those things, but the effect on the fish, coral forest is just immense there. It's even hard to imagine. And what can we learn from paleo record? So, I mean, that's what I do, but they can use a lot of the expertise that sounds that you guys have actually here. So my tools for research are big oceanographic vessels. I mean, I've been working in that area for almost 30 years, using different vessels. So the French Marion Dufresne, for example, Indonesian Barunajaya, American Ravel, Zone, so on and so forth. So it's all large cruises, you know, anywhere from months and 2 months. So we go there and we essentially recover sediments. That's what we do. Different platform. We get, you know, coring, which again, different, and a platform that we can do different coring anywhere from, you know, a few meters or even less to 100 meters if we're going with the drill ship. So depending on where we go, it will determine the time that we can reconnect. I was interested in things that happen quickly. So I went to the margin where you have big river dumping a lot of sediment. So you get an archive that is in high resolution. And my expertise is essentially in looking at those foraminifera, unicellular organism with calcitic, mostly calcitic shells. And you can see here, so you can identify them depending on what depths they are living. So some, for example, here live at the mixed layer at the warmest temperature. Other would, you know, live in the thermocline, and other really in deep water. Those we call planktic or planktonic foraminifera, those we call benthic foraminifera. So we can identify them, get them out of the sediment, and we roughly know where they live. And then we come with our different instruments and try to use chemical measurement to look at oceanographic parameter, temperature, for example, salinity, so on and so forth. And the oldest one is oxygen isotopes measurement in foraminifera. We do it with a mass spectrometer. Over here, you see the problem, those of you that know. So the equation for the isotopic equation for relating temperature to O18 is undefined. That's the problem that we have here. We have essentially one equation and two unknowns. So what do? We measure the del O18 in the calcite, or we want to know something about temperature or about the del O18 of the seawater. Why? The del O18 of the seawater tells us something, for example, on how much polar ice we have over time, or changes in salinity, whereas the temperature are already there. So for years we were limited with these things, and then came another proxy that we call a measurement of magnesium calcium in foraminifera. So we can take them, dissolve them, and measure different elements and do calibration to modern hydrography and see if any of them tell us something. So this is what I've done throughout my career. And here is an example. I mean, not the best one, but I want to show magnesium calcium versus temperature. And you can see there is an exponential relationship. So if you believe that, and it has some of, like every proxy, that's why its proxy has some issue, but overall, we can now determine independently temperature and plug it into this equation and then get, you know, the del O18 of the seawater and therefore say something about the other. So this is the tool that I've been using a lot, kind of committed because I'm the one that came up with this idea. So let's go now and look at what we know about the Holocene and the last interglacial. So what you see here is a record of CO2, carbon dioxide concentration, in the air. This is essentially extracted from air bubble in ice. So when ice freezes, it looks almost like your seltzer bottle or soda bottle that you left in the freezer. It's full of bubbles. We can extract, not me, extract the bubbles, and they actually preserve the old atmosphere. And again, what you see over the left is the carbon dioxide that we have in the atmosphere over time. And you can see that when it's higher during interglacial, that's up, okay, about 280, and then go low, high, low, high, low, high, low. That's what it is. Now we are over 400. The interesting and puzzling thing that we still argue is that every time at the beginning of this interglacial, it's high and then start to decrease into the new glaciation. You can see the arrow here, arrow here, arrow here. The only one that is different, an anomaly, is the Holocene, as far as we know, over 800,000 years. So look at the Holocene here, it start up and then boom, it start to go up. So this is one puzzling things and led and still to huge discussion whether the effect or of humans on climate started long before Industrial Revolution. Something that is highly debated and probably not accepted, but there is some truth for that. I can talk later about that. The other thing which I show you is looking at the climate. But one thing I want you to keep in mind for a second is that in the Holocene, over the last 6,000 years, carbon dioxide, the main greenhouse gases, and methane were increasing. Okay, whether we know why or not. Okay, what was puzzling to the models and the community and people that don't believe in the climate was, hey, if carbon dioxide is the main greenhouse and it's increasing, temperature should have increased. Yet most of the compilation of the temperature during the Holocene that you see here, starting at 12,000 years, going to zero, showing what I mentioned, the Holocene thermal maximum. So there is a maximum over here about, let's say, 0.6 degrees, which is a lot globally, and then it's cooling. Totally different than what one would expect. In fact, you can see it here. If you look at the same thing over here, this compilation, you can see that it's increasing to some maximum, okay, in the early mid-Holocene, and then it's decreasing. All the models that I use to predict future climate would predict, and you can see it over here at global, if you take the forcing, so radiative forcing, which is carbon dioxide, methane, and nitrous oxide, and you can see their figure over here, they're increasing, and that's, you know, the recent anthropogenic. Plug it into the models, the temperature would be increasing. So we have a problem, which we defined, you know, about almost 10 years ago as the Holocene temperature conundrum. If you want to get your paper really high at the top, put the conundrum there. It works, but really it was puzzling. And when we publish it, people jump and say, well, if you cannot even explain this thing, why would we believe anything that, you know, the model telling us to the future? Because one thing the proxies say that is, you know, cooling, and then the models basically saying that, you know, it should be warming. Why? Because if you look at what the models are saying, essentially, in the beginning, 12,000 years ago, we're still melting the ice sheet. So our albedo, the reflectance of the planet, was decreasing. So we got warming due to this. And then we have essentially the greenhouse, about 6,000 years, taking over and warming the planet, regardless of why we have that. And that's a pretty, you don't need a sophisticated model. That's pretty much a very simple radiative balance that we can do that. So people basically were puzzled. If you were a proxy, you believe in the proxy. If you were a modeler, you believe in the model. That troubled me a lot, and I decided to try to test it, and I'll show you how and why. So this is in 2016. I led an international expedition to the Western Pacific Whirlpool, and we had one course that we went especially to test this one in this area just north of Papua New Guinea. The reason we wanted there, and we were surprised, because we knew, and I'll show you in a second, that the cooling is also in the Western Pacific Whirlpool. And that's really surprising. The seasonality there is nothing. It's 28 to 28.5. It's not like where you see elsewhere. So you would not expect to see much changes there. So, but when we worked there, and my group worked on that for quite a lot of time, starting with the Indonesian and the Philippine, all those things. What I'm showing you here is just the core, but most importantly, I'm showing you temperature record. And I apologize, sometimes the left is the modern, the other is the right. It's figured from different papers. But notice that over the last 10,000 years, there is a sense of essentially cooling, very much like the global thing. And that's something that no one could deal with. Why is there cooling even in a place that today has no seasonality? So let me explain something. The Earth's climate is a slave to our orbital parameters. And the orbital parameters is the wobbling of the Earth, what we call precession, the tilt of the axis, which is what determines our seasonality, and then the eccentricity, and that is the deviation from a perfect circle. But that changed over time because of the tug of war between the different planets in our solar system. And we have this calculated for millions of years now based on celestial mechanics. So we know how it changes. And it determined the seasonality, right? So if your tilt is like this, the seasonality is bigger than if the tilt is very little. So we have expectation. And one of the things, so you see those over here, this is what we call precession, wobbling, right? That it goes like this, the planet, even though you may not feel it, right? And it determined the seasonality. So today, our seasonality is very low in, the tropics or everywhere else. 125 years ago, we have maximum seasonality due to the changes in what we call essentially the orbital parameter. They determine the amount of solar radiation coming. In our jargon, we call it insolation. So how much sun is getting us, okay? So the idea that we had is, okay, you have low seasonality here, let's go to where, but you have CO2, let's go to time that we have very high seasonality, but no change in CO2, and that's the mass integration. So this is a little complicated, but I'll try to explain. So what I'm showing you here is comparing the Holocene on the right and the last interglacial, and I'm comparing here, just to give you an idea, the greenhouse gases in terms of radiative forcing. So you can calculate what would be effect on essentially the solar and our, the solar effect from how much greenhouse gases you have, or from essentially those orbital parameters. And on the left is the last interglacial. So the first thing in the dashed line, you can see that the greenhouse gases did not change. The same, so this is just the anomalies. Whereas in the Holocene, it's increasing as we already talked. Then in the blue is the mean annual insolation, and not the scale on the right. It's about something like maybe 0 to 2 watts per meter squared. Our anthropogenic effect is something around, over the whole period since industrial evolution, about 2.5 watts per meter squared. So we are very low here, but the seasonal that you see over here, and I don't have to explain, the seasonal is much larger. We know that, Miami probably interannual is fairly constant temperature, but, the seasonal one is a large one, okay? So we wanted to see, and behind that idea was that essentially the proxies are biased towards season. So those bugs don't live the same all season, right? All year, but they have preferred season that they live and reflect that thing. And they will respond to the changes in seasonality rather than mean annual. So the interpretation that we give that as mean annual is wrong. That was the working hypothesis that we had there. So notice, as I say, the other thing is that, as I said before, during the last interglacial, the seasonality was much higher, but there was no greenhouse gases. So if they're really responding to seasonal variation, definitely they should show much higher effect. So the top is the same, and the bottom is essentially the record that I mentioned near, it's just the estuary near off the mouth of the Sipik River, one of the biggest provider of mud in Southeast Asia. So the sedimentation rate was right, and we took those bugs, those foraminifera that live at the surface, measured the magnesium calcium, and we wanted to see how we construct the temperature. So the last interglacial is on the left. You can see that the peak interglacial is about 127, and then it's cooling nicely. And in the dashed line, hard to see it here, is essentially the model, completely consistent with the model. If you look at the temperature that you see over here, during the Holocene, essentially, in this core, there was no change, okay? There was no warming as we would expect. So now the idea was, okay, if they're seasonal, we really have to come with some sort of correction. And the way we did it, we looked at the different insolation curve you have here for different months, and was looking which one best essentially match the record that we have to the last interglacial, where we have a huge seasonal effect. So let's say that this is the blue one, okay? And we can come then with a correction between the seasonal and the mean annual correction. So I won't go into the physical equation here, but you can calibrate this and come with what we call seasonal to mean to annual transformation. So you just correct it for this difference between the mean annual and the seasonal insolation that is coming. So here's an example for the last interglacial. I'm working a lot on the little ice age, so when I'm always confused between that. So anyway, here's your seasonal that we measure. We made the transformation and the cooling disappeared. It's completely flat. And for the Holocene, this is what we had for the seasonal. We did the transformation and you have warming. So now we would argue that essentially the mean annual, that what we are measuring, the proxies are seasonal. What the models are showing is mean annual. If we pick up the season from the models, we are completely consistent. So the interpretation by the proxy people was pretty wrong. So now we did it in a lot of regions that we have here, and in each of them is slightly different match to season, not surprising. And at the end of the day, again, just to show you, that's what I show you. This is big compilation paper that published everywhere, did a lot of impact, and they show the Holocene thermal maximum. This is what we found, from our compilation, strong Holocene. This is after we applying essentially this transformation. So it's completely changed the discussion. There's no more that the Holocene start with much warmer temperature, which was to begin with problematic. because there was bigger ice sheets, bigger albedo. Why would it be warmer? And now we're saying, no, actually it was cooler. It was cooler because of the ice sheets. Once they retreated, oh, sorry, we started to change it. So again, just to show you also the same thing over here, I just show you, this is the last interglacial, and that's after correction. And what really is, you see over here, this is the mean annual. And what's really important is two things. The sea level compare with those mean annual, and those trigonals over here is essentially the last interglacial. We were still arguing, but probably about anywhere from 1 to 6 meters. Some people want to push it more. Sea level was higher. When the temperature, according to us, was about 0.6 degrees, not the 1 to 2 degrees that we have. In the Holocene, you can see that essentially the temperature is changing with the sea level. So no more, if we are right, and I'm not arguing that we are right. I mean, there is a lot of discussion right now. I mean, it's all model. Ironically, the modelers, they don't like it. The proxy people like it, but it's based essentially and completely agreeing with the model. In terms of the last interglacial, it might have been warmer than before. So the Holocene has continuously been warming that we have. So just to give you a summary of that, essentially, we started with receding. So the yellow is your older compilation, which are seasonal, and this one is the mean annual. First, we have effect of receding ice, and then we have rising greenhouse, regardless of what the cause is, okay? This is not to say that seasonal are not important. In climate, the seasonal are really, really important. That's the whole Milankovitch, glacial, interglacial, if you heard, is critical about that. So I don't know how much time do I have?
You have about another half hour.
Oh, good. I'm sorry, guys. You don't have to listen to me. As I said, one of the way to look at it is in looking at the ocean heat content. That is not, it may be determined by seasonal changes because that's when we essentially get deep water formation and taking the heat, but it's insensitive to seasonality. So I've been working on that in the early, 15 years ago, again in Indonesia, and we reconstructed the temperature now, not just at the surface, but also at different depths, trying to see what happened in the Holocene. And the surprise was, so this is before we did the correction even, and I'll go back to it. So this is, you see the compilation with the Holocene thermal maximum. So that's just a seasonal now we see. That's just in the Western Pacific. Won't put that is more global. But then at 500 meter, we got that the temperature of the water is decreasing quite a lot, something on the order of about 2.5 degrees. At 900, decreasing by about 1.5 to 2 degrees. So it's a huge cooling trend. That means that your ocean heat content is decreasing. Now, Indonesia is over here on the left, but the source of the water, intermediate water, and those slightly deeper water is in the Southern Ocean. A lot of what will happen in climate start in the Southern Ocean. So think about that. The ocean surface, it's about 70% of the globe, right? But only very tiny amount is actually interacting that surface with the deep. In fact, only 4% of that. And it's mainly happened either in the Northern Atlantic or in the Southern Ocean. So what happened, but by volume, it's 95% the deep ocean. So whatever happened in those high latitude, critical to two things, the heat and carbon dioxide. Carbon dioxide is highly soluble in seawater, and whatever will happen to the heat happen also with carbon dioxide. So the source, as we see here, if something happened here, we tend to conclude that it comes from those water masses circulation that you have here in different, those are subsurface circulation that you get with this area. So it's not just a local thing. It has to happen, whatever sea in the deep ocean has to happen in higher latitude surface. So again, at that time, we saw a strong Holocene thermal maximum also in the deep water and then cooling. And when we looked in detail in what we call the common era, essentially, so how many of you have heard about the Mount Hopi State? Okay, so Michael Mann, who is probably the face of climate change in the US, if you look at TVs, he's as a postdoc in 1999, he took all the proxies, did some statistical analysis, and he showed that over 1,000 years, essentially, this is before what I show you here, climate was cooling until the last 150 years. And his conclusion was at that time, and that's what sells sometimes, big things like that, the warming in the last 150 years is unprecedented in 1,000 years. You can imagine what that did to your governance. I mean, this is not something, so what happened later, we all try to figure out what happened, I'll show you. But 20 years, it was attacked, the statistics is wrong, the proxies, the Senate, the Congress, everyone. It held everywhere. We were surprised in 2003. So here's your two compilation, MAN 2003, Moberg 2005 in those colors, and our own in the Pacific, where supposedly nothing happened, right? It's warm. Why would it go? Well, it turned out that we get exactly what they found in the Northern Hemisphere. So really, the Western Pacific warm pool is being, sensitive to climate, and you get two periods here. The one that we know about 1,000 years is the medieval warm period. Those are all Northern Hemisphere period because they are already in historical record. We know how much, the price of potato was going up and down at that time, so on and so forth. Wine, right? And it's all in the church's library. And that followed with a cooling, significant cooling in the Little Ice Age. Okay, so we know those things. And we were surprised that the deep ocean seemed to be capturing the cooling from the medieval warm period. And by the way, if you read, it's not just period. There was the Roman Dark Ages, the Roman warm. It's all historical. But the one thing that happened here, it cooled and it never actually rebounded. And that makes sense. It's a deep ocean. It doesn't respond as fast as the surface. So I published it in 2013, and I calculated the changes in the ocean heat content and then in the rate. This was just before the release of the AR4, I believe, 2013, of the intergovernmental IPCC program that we have here. And what we made an argument there, look at the fact that ocean heat content, we are losing heat, so it's cooling. And this is for today, but if you look at the rate of heat change, the current rate is much higher than was before, right? With the implication that recent global warming totally overwhelmed everything in the past. And that made, a huge response. Media went on both things completely crazy. I got, both sides, people that didn't believe it. And I got from people in the Congress and other, want to do more. I'm just saying no because my work, because they are paying attention to these things. And it's important, whatever you do and we do is actually important. So I want to finish here with precipitation that I say. So we show that the temperature changes, but it does affect, because of the moisture, essentially the precipitation. So just to go back to what we started, most of the precipitation is along, we're talking about 4 or 5 meters of rain annually. Okay, and there are 2 limbs over here. This is the tropical belt that you have, and that's another one, intertropical Pacific zone, and the South Pacific zone. One thing that over the last 10, 15 years, we realized that the monsoon, so you have different monsoon systems. Most of you probably heard about the Indian monsoon. Other may have heard of the East Asian monsoon and then the Australian monsoon. We now, and I'll show in a second, think that are all related to one global system that relate to the tropical belt. So the ITCZ, when the sun is in the north, will follow the sun and will be located mostly in the north. And then during the winter, it goes with the zenith and then go south. So ITCZ, and you get twice a year, it's moving, so you get twice a year rain, twice a year dry season. And some of the questions that we are still puzzling in modern climatology, how is it going to respond? Is it going to move somewhere, or is it going to expand and shrink? We argue on that. So on the right, you see essentially the movement that come from a satellite of the ITCZ. And on the left, you see the whole thing, but essentially we think now that the way monsoon is part of a global system and will be affected as the global system will be. And I did mention the 2 types of circulation. All I showed you right now is things that have to do with the headly, the meridional, the equator to pole, but there is the zonal, the walker that go from east to west. And that is essentially the mechanism that control the ENSO, El Nino Southern Oscillation. So the ENSO system is such that move the rain, now the convection, not north and south, but west to east. So during La Nina, El Nino, so I don't know, El Nino to those of you that don't know, it's an interannual, doesn't happen like monsoon every year or every season that we have, every few years. So it's interannual, and it's always though occur at the same time. What time does it occur?
Navidad, Christmas.
Yeah, you guys know Spanish, not me. El Nino. What is El Nino? The baby, Christ, right? So it was defined around the 1500 by the fishermen. So that's where they have a strong upwelling and a lot of anchovy, not the one that we put in the pizza, the one that we essentially feed the chicken. And they notice that sometime during Christmas, the cold water there become really warm and the fish disappear. And only when I was a student, it was also talked as a social thing, but I think since the 1990s, we started to understand the significance. There were 2 things, the Southern Oscillation, which was the atmosphere, and El Nino, the ocean, and now they're together as ENSO. So during El Nino, which is the anomaly to the normal, essentially the water circulation become weaker, and the warm pool water is moving to the east. And with that, also the convection and precipitation, that's where, southern Peru is getting quite a lot of rain in that, area and play a huge effect on development of civilization there. During La Nina, you get a strengthening of the water circulation and it push everything to the left. So those will determine during El Nino, in this case to the west, you get droughts in that's the one that I showed you with big fires, in Borneo and Southeast Asia. During La Nina, that's what you get all the flooding that you have. You can see over here, this is anomaly on precipitation during El Nino, during the summer, for example, and you can see a lot of rain over here. There are different flavors of El Nino. But you can see this area is completely dry over here. So again, we try to determine in the last few minutes, I want to show you, ask the question, how does that response over time, given the climate change that I just discussed? So this is, again, Papua New Guinea with the big river, the Sepik and the Ramu, and we took two cores over here. And we are using what's called X-ray fluorescence. So that allows you to scan the cores without doing too much work and get all the elemental composition, mainly of the terrestrial autogenous minerals. So aluminum, silicon, potassium, titanium, all this. So we want to look with that, how the input of those original material change over time. So this is what we're doing here. And this is what I'm showing you here. Again, the Holocene left is the present 10,000 years ago. And in the different colors that you see here is different elemental ratio. So the good thing is that you don't physically analyze it. You just let it scan in 2 centimeter, 1 centimeter, resolution. So you can get, in this case, almost, decadal or subdecadal resolution. Very good, which you can do when you'll need 10 graduate students for 100 years to work on that. And we can afford that. So this is what you see over here, and then in the other symbols, essentially, is measurement of foraminifera, looking at the deletion of seawater, but think about that as salinity, okay? So higher number is high salinity, lower number is low salinity. And again, we are comparing the Holocene and last interglacial, and what I want to show you here is that during the time that we talked about the Holocene thermal maximum, everything happened there. The time between 9 and let's say something like 5, the yellow over here, we have reduced runoff and higher salinity, droughts essentially. We get it essentially also during this maximum, thermal maximum during the last interglacial. So there is a period in the middle here where the seasonal temperature are warmer. There is also a major effect on the rain. Why is it? That's another question that we wanted to ask. And this has to do, again, at that time, everything is related to the amount of solar radiation coming out. In this case, you see the insolation, and we are at a minimum, essentially, precessional insolation. So a lot of that is coming from the orbital parameter. So we have to consider two options. One is that what I told you, maybe it's a north-south movement, and we just move. So the rain now is not falling right on Papua New Guinea. Or maybe we have the zonal and essentially more, I don't like it, but we call El Nino-like condition or La Nina. That's what we do. So to do that, we looked at different cores in different, and they come from different archives. So, for example, karst caves in eastern China that we have over here that we can reconstruct with isotope, a cave in Borneo, and a cave, our course in Papua New Guinea, and other over here. So kind of take the whole range of movement of the Indonesian, ITCZ, and try to ask the question, did it move north or south, or maybe it shrunk and expanded? So the way to deal with that is what we call PCA, principal component analysis, which is just a statistical way to combine everything together and have a single record, right? And see what's the common to all this. So here is what we are seeing over here. On the left is, a record of what we call principal component 1, for example. So it's mean that there is the first variable that control essentially the changes, is in PC1. So I explained 50% of the change or the variance that you see on both 80% here, 50%. And you can look at the same core locations that I show you here. The bluish thing, over here is where we get essentially more rain. And the darkest is where we have less rain. So we have less on the south, less on the north, and more in the middle. That tells us that it is shrinking or expanding. So think about that, and I talk with meteorologists. It's a very simple explanation, but I think it's close to the truth. You have the same amount of water, but if you put it in a smaller area, you'll have more, and if you spread it all over a bigger round, you'll have less. This seems to be the first, effect that we have over here. And in fact, it is pretty consistent with the models that the IPCC had, which is over here, you can see, but basically, if you read it, it says wet gets wetter, dry gets drier. Right, so that's the thing that we have. So, and then we see it now even in rain that happen, on a daily basis. When we get really hammered with the rain because the amount of moisture that the warm air can hold is much higher than colder air. The second principal component, 70% that we have here, you can see that it has a very different structure, and I don't want to belabor too long, but I'll tell you that it really fits with a lot of proxies that we have over here of the ENSO system. So the second component or effect on the rain there is also changes either in the intensity or in the frequency of El Nino Southern Oscillation that happens with climate. So those two things work together. So when you have strong water circulation, which is similar to La Nina, you get more precipitation. When you have weak water circulation, you have droughts in this area. Yeah, and that's pretty much what we have. I want to stop here, show you essentially the summary, and leave it if anyone has comments or questions. Thank you.
This is getting kind of, well, for sure, out of your time scale. But I was wondering if you could make some comparisons between the Holocene thermal maximum, the interglacials, and the last interglacial, for example, and conditions, causes and conditions a long time ago, like 50 million years or so, during the Paleocene, Eocene thermal maximum. In general, just general comparisons.
That's a good, I think the seasonality was probably lower back then. The one thing that, and I worked on that, yeah, it's hard to make a comparison, but one of the things that was really attractive, so the Paleocene Eocene, those of you that know, is about, 60 billion years ago in general. It's mid Eocene is probably the warmest period that we have, and then we have the Paleocene Eocene boundary 56 million years ago. Sorry, I'm just we have an event that will warming. And one of the questions that was interesting is, and debated a lot, how warm can the warm surface water get? There are people very smart that say, well, we can't because of evaporation and other constraints, we cannot raise it. Yet some proxy bring us to 40 degrees, which is huge. This is where we're heading. I know I'm not answering directly your question.
Well, the kinds of evidence are completely, they don't overlap, so it's really tough.
Yeah, it's hard. We don't even have the orbital parameter back then. What I was going to say that we have to, expect that some of those high warm temperature are driven by seasonal. I don't know how much seasonality we have back there. And the numbers that are coming at that are really, really warm and worried. And part of them that justify because they don't find, for example, prokaryotes that basically disappear once you autoclave there at 40 degrees for a longer time. So yeah, that's the best I can do.
It's fine.
It's a good
Thank you.
question.
Thank
It's
you so much.
absolutely, yeah, I think that's a struggle because there were one school that believed that the tropics are thermodynamically, we have a thermostat there. It has to do a lot with the clouds. Clouds really control, that's the big uncertainty in models, how clouds will do and where the clouds are, the shape and high and low clouds have a different effect on climate. So people like Ramanathan, who is like one of the premier scientists, believe that there is, thermostat there, but if the proxies are correct, then we can get to 40, then there is no thermostat whatsoever. So that's another conundrum. That's should call it the conundrum, and we'll get into the high-profile papers.
Well, thank you very much.
Sure. Yes.
Do you think diagenesis alters the delta 18 values in your forehands?
Yeah, that's a very good question. Not in these forums. In older, like the PETM, that definitely is a huge problem. Well, diagenesis can work in different ways, right? One is dissolution, and that will lower, for example, the magnesium. So it will actually give you low, but as we go older in time, we get overgrowth. So we have essentially or complete recrystallization. It's really difficult. I mean, there are ways to deal with that, and they are not complete. You can use secondary teams or, in different ways, but it is, as we go old in time, on this, I totally believe.
Yeah.
Oh, sorry.
Yeah, given that the North Atlantic deep water, when it rises around Antarctica, really gives off a lot of heat. Actually, this is where we lose most of our heat. So would there be something related to the North Atlantic deep water, which is of course coming from the Gulf Stream going to the Norwegian Sea, sinking back down there? Would there be some relationship in why the oceans is warming? That means we are not losing as much heat, or what?
So that's an excellent question. The first, the heat will go to shallower depths first, so intermediate water, thermocline. So we know different regions are responding. In the deep water, near the where it's formed, we see some in the modern observation, but very little. You see some. So the measurement, just to get people that are not oceanographer, the way we calculate ocean heat, we take temperature profile, and we have now temperature profile from 1950. Essentially, people are taking and then looking, believe it or not, less than 0.1 degree we can determine. Now we have a even automatic system, and they go to 2,000 meters. Below that we can. So we use actually marine mammals that we put essentially thermometers on them, to recorders, and they go deep and they come, and then when they go, of course, the whales have to go to the surface, then they transmit to us the profile. We also shoot different things to measure it, and then we compile all this and calculate by volume, everything else. So 50 years is not much, and the deep water, barely detectable right now. But we worked the same thing. I didn't show, I had a postdoc working on that, and we can see on the time scale that I talked about that respond within decades. So but it was also intermediate. So I think it is a big volume, but it will take a long time to make up for, take a lot more the heat. So when just to give you to answer, when I published that, my ocean heat content, I can show you, Michael Mann actually attacked me and said, well, it doesn't look like my hockey stick, so it's incorrect. He's like social media, man. I and I say, Michael, you're not an oceanographer. The deep ocean takes time. It's not like a surface. And I say, by analogy, if you ask a fish, essentially at deep water, 3 kilometers, what do you think about global warming? He actually would think that you're talking about the medieval warm period because he doesn't know what's happening now. Yeah, Michael, he got back to me and he said, okay, you're right. But it will take time, and I don't think it will solve the problem. I mean, there are the other way around that now people are trying to pump cold water, and that may happen here. If you start to get, to cool the surface, but that's crazy also.
Is there a physical reason why greenhouse gases would affect seasonality?
They were what?
Is there a what's the physical reason why, or is there one, why greenhouse gas increases in the atmosphere, would that affect seasonality?
Well, first, the greenhouse gases change on seasonal basis, right? Because we reduce them photosynthesis during the summer and then the burning. But that's it really depends where, right? In the northern hemisphere is much, I would say.
The Keeling curve, right? Mauna Loa.
Yeah. It looks like this, right? So it's not, I would say it's a force fiddler on the big thing. So
there's a simple explanation for that. That's most of the continents are in the northern hemisphere where you have the trees.
Right.
Vegetation.
Yeah, no, that's absolutely what I say. It depends on the but that, Shimon, is really small compared with what we pump into that. It's really, I mean, we went from 280, we are at 410, so we are 130 parts per million. We almost 50% increase. Whether it's a very good question, because what we are calling it, whether you change the seasonality as you change the boundary conditions. Okay, so the increase is changing the boundary conditions, and that's goes to the Paleocene. Eocene, is warm. We're not. I don't know what the models are showing. I'll have to go back and see. But I would expect there will be some effect. Yeah, because, and it's different.
Would it dampen
between the winter and the summer.
Right. Would it dampen the seasonality?
I would think so. So I shouldn't say what I say, sometimes I say I love global warming, but I don't, because I'm in the Northeast, I don't like cold temperature, but it will dampen it because the winters are getting warmer.
Yeah. Concerning the CO2, it seems to me the early results of that means the Greenland ice core.
Yeah.
Showed that the CO2 seem to follow the temperature. Do you have anything to say about that?
Yes. First, there's no CO2 record from Greenland, so it's in Antarctica. Because Greenland, you have a lot of calcium carbonate dust, and then when it dissolves in the water, it generates. But you're right, in Antarctica, it has confused everyone But it's also, one thing is, there are different ages, so the bubble and the ice are not exactly the same age. But by and large now, we know what we call the seesaws, that most of the heat is getting to the northern hemisphere, into the North Atlantic, so the Gulf Stream and things that you guys coming essentially from the southern hemisphere. So it's delivered all the way. And if you sail, for example, from New Jersey and go northward, you see the Gulf Stream basically bringing that. But if you stop the circulation, then the heat is staying in the south and the north is getting colder. So I was in an expedition in Norway in 2004 for, with my group. And when I come, I have a message on my phone and it says, this is journalist from something. Can we talk about the day after tomorrow? And there was no internet back then. And I said, I barely know what I'm doing today. And I call, I said, why you care what I'm doing tomorrow? I said, oh, this is the movie, right? And so if you didn't see the movie, that's what happened. When we stop the circulation, the heat is staying there. So during glacial period, when circulation was inhibited, the south was warming when the north. So it's an artifact of this seesaw that we get at that time. So that's why it looks like. Now, that doesn't mean that CO2 is driving all the change. I don't think it is, but I think once you start to have CO2, then it contributes.
It is mainly the heat budget that you were saying about the Milankovitch cycles, isn't it?
So what happened a lot, and we are thinking about that, is everything relates to the winds, a lot of the stuff. So in the Southern Ocean, in the wind, the southern westerly wind, so the wind belt, which is the southern hemisphere equivalent of the jet stream, when that moves, it also causes upwelling in the southern hemisphere and brings heat and CO2. So why is it moving? It has to be something that has to do with orbital parameters. So that difference, we can reconcile it, and Milankovitch still alive. We tried recently to challenge it in a paper, it didn't go very well.
I can see that's even in the Cretaceous.
Yeah, but we know it now that in some cores, the difference is, it's true, the warming is starting before the CO2. There is something that triggers a starter that started before, but once it goes and the CO2 start to release, it has an effect. So I've never been a fan of a single factor. We are trying to find one that explains everything that doesn't work. Nature is complicated. And so I think you get, and this is a huge debate now on the CO2 increase at the late Holocene. People don't like, and probably it's incorrect, the fact that it's driven by human. And by that, they mean all the deforestation and cultivation of rice everywhere in Southeast Asia that started about 6,000 years ago. That's probably caused the methane to come, but there are other things that probably happened.
Otherwise, all those past climate going down to the Cambrian will be triggered by CO2, if this is true.
Well,
When we look at the Milankovitch cycle, it seems to me that the Milankovitch cycles are the main driver.
well, I do think so. Back in time, people didn't believe Milankovitch before the ice ages, and now we see it all the way going millions of years into the Cretaceous. CO2 is not the only one, right?
Well, we are enhancing.
I'm sorry?
It enhances it probably, but not the main triggering factor.
Yeah. I think it's often, in my opinion, something else can start it, right? But it's not who started, it, who has the biggest impact, and CO2 has a very big. Once you go back in time, plate tectonics, it's a completely different talk. I can give it. I have it ready. But what controls CO2 on long time scales? If you in geology, the main paradigm is that it's a balance between CO2 release from plate tectonics, so along ridges, volcanism, that's what releases it. And the CO2 goes to the atmosphere. It interact with water, make carbonic and sulfuric acid and all this. And the weathering of silicate rock is what driving. And many people, much smarter than I am, and there are many of those, that believe that the world is in some sort of a balance, right? So if you have more CO2, then you have more weathering, and we always kind of keeping us. I don't subscribe to that necessarily right now, and but that's on long term, right? You start to look. It's not the ocean. The ocean is good for 100,000, not for million. Then you start to have geology and biology and other stuff. I mean, it's a different story. Most of the people they don't like to believe that the earth is not having some negative feedback that keeping us in the Goldilocks situation. I don't want to go, this is a whole new seminar, but I would say that the lowest CO2 possible ever was 20,000 years ago. So there are ecologies. What happened in 150 ppm to terrestrial plants, C3 plants, for example? They shut up. It's a compensation. You can't have photosynthesis. So we are in the lowest.